So this is a new section. So far you learned permutations and combinations. So there's quite a bit power that those two gives you. You can now calculate many things. But okay, so you learn permutations, which choosing people and putting in a line to take a picture. You learn combinations, which means number of ways to choose people into a committee. So you're choosing them in a non-ordered way. But even with these two techniques, you will see that in many questions, you still cannot write a formula using these techniques. So one of these questions I will write now. We'll talk about how to solve in a straight way, and then we'll develop a formula out of this. The formula we develop will be called combinations with repetition. Some of you may know this already, but I think it's still interesting to develop this from the basics. So this is a story problem that you should try to understand the whole story. So on their way home from track practice, 7 high school students stop at a restaurant where each of them has one of the following. They can have a cheeseburger. So this is what's available on the menu. They can have a hot dog. They can have a taco. Taco is a kind of food like the other ones. It's a more Mexican food actually. Or a fish sandwich. So we have 4 different things on the menu that they can choose to eat for a meal. So how many different ways they can do this? How many different purchases are possible? Here is the key thing. From the viewpoint of the restaurant. I mean, most of the time we won't be saying this. But to emphasize that, it is not from the viewpoint of the group, but from the viewpoint of the restaurant, which makes a whole difference. Why it makes a whole difference? Because you can start thinking about this. We don't want to know who is eating what, basically. The restaurant doesn't care who is eating what. And the restaurant doesn't know the names of these people. All they care about, there are 7 high school students out there eating these food. So they don't care anything about who ate what and how many, they don't care about this. And everyone orders one dish. Okay, they don't order 2 dishes. So one student doesn't decide to eat, I'm going to eat cheeseburger and hot dog at the same time. They only eat one of them. So how many different ways we can do this?
Can they get no cheeseburger as well?
No, they need to eat something. They don't have to buy a cheeseburger, yes. So everyone may eat fish sandwich. That's one of the choices. That's 7 fish sandwiches. That's the order. Bring us 7 fish sandwiches. That's the order.
7?
Huh?
4 to the power 7.
4 to the power 7. That's one of the answers. It's actually a good answer, but it's a wrong answer, but it's a good answer. Why it's a wrong answer? It's a good answer because it's one of the things we should be thinking about before anything else. Why not multiply 4 different choices? We have 4 different choices, 7 times to get the answer. Why not do it?
10 factorial and 3 factorial times.
So another answer. 10 factorial, 3 factorial times 7 factors. That's another. Can I say 10 choose 3? 10 choose 3 is another answer. Much smaller number though, right? Is that your vote? That is the answer?
The way. So for example, you can divide 4 box cheeseburger. Take over this time.
You're actually giving that. Yes, this is the correct answer, and her argument is what we are going to do. So keep that in mind. I'll come back. This is the right answer. First, let's see why this is not the right answer. This could be a right answer to something else, a different question. Like if we don't have this question in this way, this could be an answer to that. So what does this count? Can you tell me why this is what does this count and why it can't be the answer to this one?
This counts is in this selection. What person
Eats what? Yeah.
matters.
So if we number the students, if they have the names, and if we want to know who is eating what, so like student 1 eats hot dog, student 2 eats hot dog, student 3 taco. If we want to know exactly which student is eating what, then you could think this as an experiment which has 7 levels, where you're choosing a menu item for the first student, which can be done in 4 different ways. Then you're choosing a menu item for the second student, which again can be done 4 different ways. So you can multiply these. But multiplication will result all the tuples, like all sort of 7 tuples with H and T's in it. So that means it will be recording the information that who's eating what. But we want to only count orders, not who is eating what. So let me explain this a little bit more. So order means only thing the restaurant cares about is what the waiter brings them, right? So what does waiters does? They just record the. They just want to know how many of each items is being ordered. So we have, say we have a cheeseburger. So suppose that use the letter C for it. We have the hot dog, use the letter H for it. We have taco, use the letter T for it. And we have the fish sandwich. And use the letter F for it. So with seven students, possible orders are like they could be ordering cheeseburger, 1 hot dog, 2 tacos. Instead of writing 2 tacos, let's do TT and F. This is one of the orders. 3 cheeseburgers, 1 hot dog, 2 tacos, and 1 fish. So it doesn't matter who is eating what. So this is one of the orders. And in the same way, this is another order. 4 cheeseburgers, 3 hot dogs. That's all they are eating. They don't eat any hot dogs. They don't eat any tacos or fish. Or you could do this. No fish, but 2 cheeseburgers, 2 hot dogs, and 3 tacos. That's the order. So these are the things that we're counting. We're not counting who's eating what. So we're not counting tuples of these things. We're only counting all possible ways the waiter can take the order and put it on his small piece of paper, right? So in that sense, how many different ways I can write these CHTs? That's the question. And the answer is this one. But again, we have to do one more step to get to this. So I will tell that step too. So to get to this, 10 choose 3, doesn't look like there's any 10s there. To get to this, we have to do one more logical step, which means, suppose that the guy is tired of, the waiter, woman or man, waiter got tired of writing C's and H and found a very smart way of writing what the exact order is. So the waiter decides to put circles and crosses to mean what the order is. Circles and crosses. Sometimes they do it with the T and stuff. Yeah? So what the idea is that he puts circle and crosses in such a way that he wants to record how many each of them is ordered by putting zeros for the number of times that item is ordered. So he puts zeros before the first X to mean number of cheeseburgers. And then he puts either 0 or nothing to mean the number of hot dogs. And here he puts T's for the zeros for the number of tacos. And at the end he puts zeros for the number of fish. This is a good way of recording it. See, this one will be 0, 0, 0, x 0, because I have a hot dog, x 0, 0, cross 0. Once you memorize this, it's very easy. 0, 0, x 0, 0, x 0, 0. So the waiter uses this recording process. So hot dogs, and then cross and cross. There is no other things. Get used to it. I mean, you just have to remember it's CHTF, right? So if you see H and then T and then cross. Now, does everybody see that this will be unique way of writing the order? That you cannot, like that means if you see this, you know exactly what the order is. As everybody sees that. This tells you exactly what the order is. So the rule is, look at the zeros before the x's, between the x's. So this means this many C's, this means this many H, this many T's, this many F's. Count number of zeros. So if you're having any doubt about this order will not be converted to x is 0, you can tell me that order. Is there any order that I cannot write this way? Any orders that you can see? No, right? So every order can be written this way. So now we come back to the answer. So you said the x's and zeros. So we came to x's and zeros. So from here, why did you say this is the answer?
Because from school, I must say, we have 4 dots and 3 boundary points like x's, and the other things are considered just zeros. So we have 4 minus 1 boundaries, x's and 7.
Can I also say it this way? Say it.
So we use this combination as a permutation.
Mhm.
And as we know from previous lessons,
Mhm.
10 factorial over 2 factorial.
Mhm. The interpretation with this one, what's your name? Sorry. Didem. Didem? Didem said it's equal to this because this is like Masasauga question, where you have a word with length 7 using 2 letters. So you're using 5 zeros, 3 x's. 7 zeros and 3 x's. So he says, says, you have total of 10 items, 7 of them are zeros, so this is 4 zeros, and then 3 of them is x's, totally 10 of them. So this is number of ways you can write a word using 10 zeros and 3 x's. That's why equal to this. Right? Right? We did this before. We did the Masasauga problem, where you repeated ones had to be divided by the factorials. Also, which I wrote there, this is same as 10 choose 3 or 10 choose 7. You can use either of them. You can interpret it saying that you have available 10 spots, and you need to choose where x's will be. So you're choosing 3 of the numbers. The spots are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are these 10 spots. Did I? Bunda bir tane fazla x var galiba. Şurada bir tane fazla var. So these are available spots. And exactly number 3, number 6, and number 10 are the ones you have x on. So that means we are choosing 3 of the numbers out of 10. And they are choosing them unordered way. We are choosing 3 numbers out of 10. So it's done 10 choose 3 way. Or you can interpret it as you're choosing places where the zeros are put. So you're choosing 7 places for zeros. So in either case, use 10 choose 7 or 10 choose 3. This is the answer. This is how you solve it. We're going to develop a whole technique out of this. But before doing that, I write one more question. Okay, this is a question very similar. An investor has 25,000 to invest among 4 possible investments. Each investment must be in units of $1,000. If the entire amount is to be invested, how many different investments are possible? So we have $25,000. We are going to invest this on 4 different investments. We want to finish it all. And we have to invest on multiples of 1,000. Because if it wasn't a multiples of 1,000, this could be a much harder question, right? Because you will be looking into exact figures of point zeros and point ones. We don't want that. So it's multiples of 1,000. We have 20,000 and 4 investment locations. So how many different ways I can invest this 25,000?
28 factorial over 25.
So this is one of the answers. Is this a correct answer?
I think 29.
Huh?
29 factorial.
29 factories, another. Divide by 26 or 25? Okay, we have a competing different answer. Why 29?
Because you can also do 0.
0. Maybe. But in neither of these, you need a good, clear explanation. So what are we doing exactly? So what are we choosing? So can we state this problem as a problem of counting some x's, zeros, something that more familiar with? See, the thing that you should be gaining out of this course is this kind of strategies of problem solving, right? At the end, it's not important maybe what the formulas are, but how you approach to solve these problems, right? So you're learning a strategy of converting it into something else, right? Crosses, x's. So it's important to think that way too. Mm-hmm.
Divide the $20,000 and $5,000 into 1,000 banknotes, for example.
Uh-huh.
And we use 3 indicators so that
Uh-huh.
we can implement that repeated permutations.
But we don't know formulas for repeated permutations. This is the way we are going to get to there. So, but you're right. We have 25 coins. These are identical. It's important to note a statement like that. And we have investment places. We have 4 boxes, which are not identical. They are distinct. These are probably different investment options, right? So they are numbered 4 boxes, but they're distinct, 4 distinct boxes. So we have 25 identical things and 4 distinct things. Remember we talked about how these identicals and distincts are important. So the problem is how many different ways you can distribute 25 identical things in 4 distinct boxes. That's fun. Yeah, it's exactly that problem. So how many ways I can do this? I can also say, this is one of the ways to it. Another way to see it, this is also a very nice way to convert all these problems. I love this way, is this. Imagine you're looking at integer solutions to this equation, where you allow xi bigger or equal to 0, an integer. How many different solutions are possible? That's the exact same problem, right? So if you have a solution, like say 5, 10, 10, 0, that means you put 5 coins here, 10 coins here, 10 coins here, no coins here. So no is a possibility. Now we need a third way of looking at it, which will connect this to the previous question. Can this be also a third way to see it? 20 students ordering 4 menu items. Can it be also that? We had 7 students going and ordering 4 things. Suppose you have 20 students going to the restaurant and ordering 4 menu items. So number of coins goes to here is exactly number of cheeseburgers. Number of students that order cheeseburgers. Number of hot dogs, number of tacos, number of fish. It's the exact same question. 20 students ordering 4 menu items is equal to both of these questions. That means I can also say, this is the fifth way. This is exactly the same as number of words with 20 zeros, 3 x's. Because you need 3 separators. So this means investment 1, investment 2, investment 3. So coins, actually, circles, are exactly your investments. Number of like $1,000 you invest on the first thing. And the crosses are separators.
Aren't there supposed to be 25 students?
Oh, sorry, 25. Sorry, I 25, yeah. Thank you. Somewhere I missed the 25, yes. So it's 25,000 or something, sorry. So everyone is following so far? The 25, 25, 25, they're all same numbers. But you see the same question in different forms. It's actually good to remember that if you know how to approach the one of them, you can always convert other ones to that one. So if you like this one, for example, you can always say, all of these questions like this, and I know the formula for this. For example, I like this one. It's my personal choice, I don't know why. I always convert everything to this one. You can also like this one. This is also another good one. You can convert all of them to this one and say, I can count these. Okay? So what is the answer? We already counted this, right? So what's the answer for the number of words which has 25 zeros and 3 x's? 28, 25, 3. So it's like 28 choose 3 or 28 choose 25. So your winner is the first number. So this is the correct one. This one is not correct because 0 is already included into possibilities. Okay? So let's be the big cross. So that you don't confuse it. Okay, so any questions you can ask now. Otherwise, I'm going to do something else. I mean, something else related to this. Any questions? Okay, so so we had so far 2 formulas. This is your third formula. So this is formula for repeated combinations. So the number of ways to distribute, let me use AND objects, but let me check. number of ways to distribute n identical objects, so the balls or things, into r distinct boxes is. So this is exactly what we had so far, right? So n identical is n is your 25, 4 is your distinct boxes. So the answer to this divide by this. So you have one less cross than the number of boxes, because yes, separators is r minus 1. And you can write this as n plus r minus 1, choose n, or equivalent to, you can write it as choose r minus 1. Remember, the r distincts makes it n zeros and r minus 1 x's, because you need separators. R minus 1 separators. Some of you know this as a repeated combination formula probably. This is the repeated combinations of choosing n things. Sometimes you can be stated like that, with available more options. I don't like that, so I'm not going to insist on it, but some people think you're choosing n things, but because you're like multiple access to the boxes, I don't like this, but think this way. You have n balls and r places. So for each of the ball, you're actually choosing a box. So this n is like the balls you're choosing, but then boxes, you have r boxes, but you can choose a box again and again. So the boxes are infinite source. So you can choose a box again and again. So you're actually adding up the number of places you can choose. But it's really not a good way of approaching it. So I will say, approach to these problems, always try to see what 0x sequence you can find out of it. And then write exactly the formulas from using these 0x sequence interpretation of the question. Okay, so let's solve this question again by taking this out. Suppose that we don't need to spend all the money. How many different ways you can invest $25,000 into 4 different investment possibilities? So this is your second type of question. So what should the answer be? 29. Choose 4. Good. This is the first answer we got. Any other answers that you can give me? Okay, this will be the last question we solve today. We have so as I said, let me solve it using one of the interpretations. So the answer is same as the number of solutions to with xi bigger or equal to 0 for all I. Number of integer. Suppose you're looking at integer solutions to this equation. with equal 25, we solved it. But now we don't have to invest everything. So that means it's now sum of them less than equal to 25 is what we want to solve. And we, again, invest nothing in some items. That's possible. So how many solutions to this equation exist? This one? Why 29?
Because we can never
Uh-huh. Okay, so let's do this. Let's call this solution 1. I like this. These are the investment number of dollars, $1,000 you're going to invest, and the investment 1, investment 2, investment 3, investment 4. Suppose let's keep another dummy variable, x5, and this is number of $1,000 to be left in the account. So not invested to anything. But if you don't invest everything, if you have one variable for what is left, the sum should be 25. And now all of them are positive or equal to 0. So this is exactly the question that you have 25 coins to be distributed to 5 boxes. So the answer is, so we have like 5 places, so that means 4 x's and 25 zeros. So the answer will be 29, choose 4. So the answer is correct. Thanks. But this is not a normal person will approach to this question, right? What is a normal person will approach to this problem? Like a normal means if you are in a sort of a normal day, you say, okay, I want to know this is less than 25. First you will do it for 25. Then you will do it for 24. Do it for 23. So why not? Make it equal to any number less than 25. So this is solution 2. Solve this for all the k's less than equal to 25. Right? So for 25, what the answer will be? So you're solving this equation. Now you have 3 x's and 25 zeros. So the answer is 28, choose 3. This is for 20 equals to 25. Let's solve this for 24. So you will be summing these up. Now 3 x's, 24 zeros. And the answer will be 27. Choose 3. If I drop this k slowly, I will be getting all these numbers 28, 27, 26, 25, 23. So my answer here suddenly will be something like this. This will be 29, 28, choose 3, 27, choose 3, 26, choose 3. The worst case scenario, you're investing nothing to 0. But you will have 3 crosses and 3 chooses. So you'll be choosing 3, choose 3. We found something strange. we found that such a long sum is equal to this. Does this make you remember any of the things we had last time? What was the...
Peki, ben ikisinin toplamı 28'in 4'üsü ediyor. Daha sonra
So remember I asked this question or formula. We said that R choose R plus 1 choose R. If you have always the R's here, N choose R is equal to N plus 1 choose R plus 1. And I said, can you find a combinatorial argument to prove this? Now we found one. We found one that you can actually count number of solutions to equal less than equal to n with R items, and you can count that first using a dummy variable, and you will get this answer. Second, without using a dummy variable, by doing it for all the case smaller than n, and you get this answer. So this is actually a number of solutions to this equation with the positive answers. So this is number of solutions. And if you do it two different ways, this is one of the ways you get. Did I write it correctly? 20. Yeah. So this is R plus 1. Yeah, because we have plus 1, we have to put a plus 1 here. You have to, you have to set it up in a different way to just get this. You have to set it up slightly differently because you want to get this to be equal to n plus 1. But this is essentially, it's true. So it's a number of solutions. One way to solve it by using a dummy variable. The other way is solving it by using a different values that you can choose. And you have to be careful about how to set this up. But this is the correct way. So you see that very unexpected problems can be a good source of finding these kind of equations. This is one way to get an equation using a combinatorial argument. This proves it by a combinatorial argument. Any questions on this before we finish? No. We are not done yet. But on Fridays, I sense that there's a little bit tiredness in the air. We can add some excitement to it. If you want, we can give a second quiz or something. Is 2 hours too long? I mean, okay. Today I won't give you a homework. I will give it on Tuesday, and then we can do it on the next Tuesday or Friday according to your choice. But I'll not assign you a homework today. But this is a material that is in the book. Lots of questions there. So go study. It might be too late before the exam, okay? So don't leave this to the end. And have a good weekend. So,